Alrighty, in this video we're going to talk about the shortest distance between two lines, and it really depends on what those two lines look like. So for example, if the lines are already two lines that are intersecting, you can pick any point on the line. So let's pick this point on the first line and then this other point on the second line, which is literally the same point because they're intersecting. Here the distance is 0 because those lines are actually touching. Similarly, if you've got coincident lines where they're sitting on top of each other, then the distance is 0 because you can pick any point that is just sitting in that same spot on both lines, and again, they're touching. If you've got parallel lines, it's a bit weird because you can pick a point here, for example, and find the shortest distance. But if you picked up other point here and found the shortest distance, those two would be equal to each other, those distances. So that actually comes back to the last topic, which was shortest distance from a point to a line. And for example, if we had a situation here where maybe these two lines are parallel, all you would have to do is pick any point on the blue line, like this one, for example, and find the distance, and it would also be that shortest distance. So you just pick a random point and you use the method from last time. Where it gets really interesting with two lines is where the lines are skewed. Now there's quite a process here, and I'm not going to lie, it's not pretty, but we will make it through. Essentially, what you need to do is find the cross product first. So that's what we'll look at. We take the two direction vectors from these two lines. So in this case, the direction vector comes from the numbers in front of the t. 1 minus 1 and 1 gives us that first vector. And then the second direction vector comes from the second line. Next thing we need to do is work out the cross product, which is v crossed with w. So that's doing this big determinant, I, j, k, 1, minus 1, 1, and minus 1, 2, minus 1. Now I won't do the full steps working out, but you can sort of imagine first thing we're going to do is break off this subdeterminant here to get our first entry of the vector. So that's going to be minus 1 times minus 1. So that's 1. Take away 2. Next thing is going to be the outer determinant. So I'm going to get 1 and minus 1. So minus 1. And then I'm going to be taking away the other two. So I'll be taking away minus 1 and 1. Which is just, that. Last one we're going to get is sort of the determinant on the left. So we'll be looking at that determinant. So we're going to get 1 times 2, which is 2. Take away positive 1. So we get something looking a bit like that. And then we can simplify that down to minus 1, 0, and then 1. So that is our cross product between those two vectors. Okay. Next thing that we need to do is we need to be talking about this vector a through to b. Now the vector a through to b is basically the vector that you get when you pick any 2 points on that line. So a point on the first line is going to look like this. It's going to look like t, 1 take t, and 2 plus t. And you can sort of imagine if we look, this L1, this point here is A, and it's going to look like T, 1 take T, 2 plus T, just there. And I might underline those in red so we can really see that. Then we've got this other line here, L2, which may be skew. And we've got this point B, and the B follows the coordinates of line 2. So 3 take S, minus 1 plus 2S, and 4 take S. So if we want to find the vector from A to B, we literally just do the coordinates from B minus the coordinates from A. So that's going to be like 3 take S, take away T, then minus 1 plus 2S, take away 1 take T, and 4 take S, take away that. Now I just underline these in blue as well so you can sort of see that's coming from the B points and the red ones are coming from the A points. So this is the vector AB, and what we can do next is actually just simplify it down. So that's exactly what we're going to do. So we're going to go 3 take S take T. It's going to be that first coordinate. Our next coordinate, minus 1 and another minus 1 gives us minus 2, plus 2S plus T. And then our last coordinate is going to be 4 take 2, so 2. Take S, take T. So this is the vector AB. All right. Now, it's AB is supposed to be parallel to this V cross W vector that we found before. Because if you sort of imagine it as a picture, V cross W would be pointing in this direction that's perpendicular to both, and you would want to be perpendicular to both those lines if you're going to be finding that shortest distance. That's sort of how we define this, really. Okay, so if AB is parallel to V cross W, what does parallel mean in vectors? Well, it means that AB equals some multiple, let's call it K, of V cross W. So therefore, let's step this out as vectors. I'm going to swap to vertical mode just so we can keep track of everything. So this is the vector AB, and it equals K, lots of that other vector we found, V cross W, which is -1, 0, 1. All right, so now we can step this off into 3 equations. So let's break this up. So I get 3 take S take T equals -1 lot of K. I get -2 plus 2S plus T equals 0, lots of K. And I get 2 take S take T equals 1 lot of K there. Okay, so these are just some equations that I can solve simultaneously. It is going to look real nasty because we've got 3 equations and 3 unknowns. But let's arrange all 3, and we're going to get sort of K first, S, then T. So this becomes K take S take T equals -3 from the top equation. The next equation, there's no K, so I'm just going to go 2S plus T equals 2. And then the bottom equation, I'm going to get -K take S take T equals -2, just there. So we'll label these 1, 2, and 3. Now from here, you can just whack it in an augmented matrix if you want. 1, -1, -1, -3, 0, 2, 1, 2, and -1, -1, -1, -2. Although we don't know how to solve augmented matrices in a 3x3 system yet, we will learn that later on in the topic, but it may be hard. Let's maybe see if we can solve these just by finding a cool little trick with this. Probably what we could do is we might be able to take equation 1 and we will subtract off equation 3. So let's see what we're left. Well, K take away -K. And then I get plus -S take -S plus -T take -T equals -3 take -2. Lots of minuses here. But essentially that just becomes 2K. Everything else goes to 0 with the S's and the T's. And then that becomes equals -1. So what we're going to get there is hopefully that K equals 1/2. -1/2, sorry. All right, so we've got a K value, which is going to help us a lot. Now that'll sort of help us get our S and our T values. So K equals -1/2. Equation 1 will become, actually I can just rewrite all of our equations really. So K is -1/2. You're going to get -1/2 take S take T equals -3. You're going to get 2S plus T equals 2. And you're going to get -1/2 take S take T equals -2. If we rearrange those, what we're going to get is we're going to get -S take T equals -3 plus 1/2. Then we're going to get 2S plus T equals 2. And then we're going to get -S take T equals, again, -2.5. Which, yeah, that works out. So at this point, I can just basically cross off that bottom equation because it's a duplicate of the top one. And now let's work with equation 1 and equation 2 to find maybe S next. So probably the easiest way to do these is just to literally add those together. So 1 plus 2 is going to be -S plus 2S is S. And then all this would give you -0.5. So I got my S value. Now I just sub it in to find my T value. So maybe from equation 1, -S take T equals -2.5. Therefore, -0.5 take T equals -2.5. Therefore, -T equals -3. Therefore, T equals 3. So now we sort of have it. We have our S, K, and T values. Now we just need to think about the vector AB in terms of our S, K, and T values. So S equals minus 0.5 and T equals 3. So let's think about what AB was again. It was this vector here, which I might even be able to just borrow. There we go. AB was supposed to be that vector back there. So let's plug in all the values that we know. I'm going to get 3 take minus 0.5, take another 3. I'm going to get minus 2 plus 2 times minus 0.5 plus 3. And I'm going to get 2 take minus 0.5, take 3. So that gives me 0.5 on the top, it gives me 0 in the middle, and it gives me minus 0.5 on the bottom. So that's really good. Hopefully that seems to check out all good. So yeah, so this is the vector AB, and similarly to what we did with point in the line, the actual distance itself equals the mod of AB. So that's going to be square root of a half squared plus 0 squared plus minus a half squared, which ends up being square root of a quarter plus 0 plus a quarter, which is square root of 2 quarters, or square root of a half, or if you really like, 1 over root 2 is the distance. And if you really want to know what the distance is, it is about 0.707 when you put that in a calculator. Let me just make sure I'm not lying to you. 1 over root 2 is about 0.707, so that's good. That's pretty much how you found the distance between skew lines. It's extremely, extremely painful. It involves solving 3x3 simultaneous equations. I will note that if you want to go from this point here, polysolve on your calculator, or I think it's called like simultaneous equation solver on a Casio, will do that automatically for you. So don't feel like you're stuck and you have to do it by hand. You can use technology to help you out quite a bit here.